In this video, I will present some examples of functions that are continuous but not differentiable. How may a function fail to be differentiable? We know that if a function is differentiable, then it must be continuous. I proved this in an earlier video, which I will link in the description, so any non-continuous function will also be non-differentiable. However, it is more interesting to look for examples of functions that are continuous but are not differentiable. As a reminder, saying that a function f is continuous at a number a means that the limit as x approaches a of f of x is f of a. Saying that f is differentiable at a means that a different limit exists, the limit of f of x minus f of a over x minus a. This is the limit we use to define the derivative f prime of a. So saying that f is not differentiable at a means that this second limit does not exist. This second limit, like any other limit, may not exist for a variety of reasons. I am going to focus on two specific ways in which this limit may not exist. Because the two side limits are different, we will call this a corner, or because the limit is plus or minus infinity, we will call this a vertical tangent line. But of course, there could be other reasons why this limit does not exist, and any way in which this limit fails to exist still gives us a non-differentiable function. To understand these two special cases, I will look at one example of each. For my first example, consider the function f, defined by f of x equals absolute value of x. I want to know whether f is differentiable at 0. Let's try to compute the derivative at 0, as the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Using the definition of f, this is the limit of absolute value of x over x. Since we have the absolute value of x, it is easiest to break it into two cases. When x is positive, as x is approaching 0 on the right, the absolute value of x is simply x, and the limit is 1. On the other hand, when x is negative, as x is approaching 0 on the left, the absolute value of x is minus x, and the limit is minus 1. In conclusion, the derivative at 0 does not exist because the two side limits in the limit definition of derivative are different. Remember that derivative represents slope. I can interpret this by saying that at 0 there is a slope on the right and a different slope on the left, so to speak. And yes, that is what the graph looks like. The slope at 0 seems to be 1 if I look at 0 from the right, and minus 1 if I look at 0 from the left. The graph has a sharp edge, a corner. And in general, a function f will have a corner at x equals a when f is continuous at a, but the limit in the definition of derivative f prime of a does not exist because the side limits are different. For the second example, I will look at the function g, defined as g of x equals x to the 1/3. I want to know whether g is differentiable at 0. Again, I try to compute the derivative g prime of 0 from its definition as a limit. Using the expression I have for g, this is the limit as x approaches 0 of x to the 1/3 over x, which is the limit of 1 over x to the 2/3. This limit is infinity because the denominator has limit 0 and is always positive. Now, remember that derivative means slope. What does infinite slope mean? A line with infinite slope is a vertical line, so this suggests the graph has a vertical tangent line. And indeed, this is what the graph looks like. More generally, I will say that a function has a vertical tangent line at a point a when the function is continuous at a and the derivative at a, computed from its definition as a limit, is plus or minus infinity. In the example it was plus infinity, but minus infinity could also produce a vertical tangent line. We are not done yet. There is a little bit more to add to the concept of vertical tangent line. Let's go back to the example. I can look at it in a different way. Whenever x is not 0, I have a formula for the derivative g prime of x. Using the power rule, it is 1 over 3x to the 2/3. And then I can calculate the limit as x approaches 0 of g prime of x. And this limit is also infinity. Perhaps you find that this second calculation is easier than the earlier one. However, a priori, these two quantities, the derivative at 0 and the limit as x approaches 0 of the derivative at x, could have been different. They turn out to give the same result for this example. What's the relation between these two conditions in general? It is possible to prove that the second condition always implies the first condition. I won't write a proof right now. It is an application of L'Hopital's rule. To be fair, In practice, for almost all the functions we commonly work with, these two conditions are the same. But if we really insist, we can construct some unusual functions that satisfy one but not the other. So what do we do with this situation? The correct definition of vertical tangent line requires the derivative to be plus or minus infinity. Requiring instead the limit of the derivative to be plus or minus infinity is slightly stronger. But that is helpful. If you're working with an example and you prove it satisfies the second condition, then you have also proven it satisfies the first condition, so you have a vertical tangent line anyway. And that's what we do in calculations most of the time in practice, because it tends to be easier. Alright, that was probably a longer explanation than you care for, so I will just finish with a quick word of caution. A vertical tangent line is not the same as a vertical asymptote. I do not know where this error comes from, but I have seen it often in students' papers. In this graph, the function h has the vertical asymptote x equals 0. Notice that the function itself is not defined at 0, the limit of the function h itself as x approaches 0 is infinity. By contrast, in this graph, the function g has a vertical tangent line at x equals 0. The function itself is perfectly well defined and continues at 0. It is the derivative, g prime, which has limit infinity as x approaches 0. So don't confuse vertical asymptote and vertical tangent line.